right, hello everyone. Welcome to our very last session of the Sea Grant Educator Helpline. My name is Kristen Gehring and I am one of the education assistants here at the South Carolina Sea Grant Consortium. This is our last in the series of ocean literacy principle education resource videos. We are on the 7th of 7 ocean literacy principles. This is a helpline, so in addition to me standing here explaining some different activities that you can do with your kids or with your students, there's also Evie Bell, who is our marine education specialist, in the comments, answering any questions that you have and linking the activities that go along with what we're going to be talking about today. So like I said before, this is going to be all about ocean literacy principle number 7, which I have posted on the wall behind me. This principle is one that's near and dear to my heart as somebody who loves to study the ocean, loves to learn more about it. This one is the ocean is largely unexplored. Now, if you remember back to our very first ocean literacy principle video back in, I think it was in April, maybe early May. It's been a while that we've been doing this. If you remember back to that video, looking at the globe, we have one ocean with many features, and that one ocean covers 71% of the Earth's surface. We have an ocean-dominated planet. So even though it covers the majority of our planet and accounts for a huge amount of the surface of the Earth, we've only explored about 5%, actually a little bit less than 5% of the ocean. And that's not just taking into account the surface of the ocean, that's also taking into account the depths of the ocean as well. So even though it's 71% of the surface, if you take into account all of the surface area underneath the water's surface, it's a crazy amount of area to cover, which is why we've only explored less than 5% of it. Today we're going to be talking about some of the challenges that people face in exploring the ocean. We're going to talk a little bit about some technologies that are being used, and we're going to go through some hands-on activities to maybe do a little bit of exploring yourself. So our very first one is going to be from a NOAA education lesson plan called To Boldly Go, and it's all about why we care about ocean exploration. So Evie's going to be linking that education lesson right up in the comments where you can follow along or look back at it in the future. But one of my favorite activities from that lesson plan is one that talks about the reasons for exploring. So they lay out 7 modern reasons for exploring the ocean, and I'm going to read them out here since I don't have them all memorized. But those 7 modern reasons for ocean exploration are climate change, energy, human health, ocean health, research, innovation, and ocean literacy. So those are the 7 modern reasons. There's all kinds of reasons that people have explored the ocean throughout human history, but talking about today's world, those are some of those modern reasons that we would want to explore the ocean. So for this activity, all you're going to need are a couple pieces of paper, some scissors, and maybe some tape or some glue, and you're going to be constructing these learning shapes, kind of like a fancy die. In that lesson plan, there is a blank learning shape. This one has some example writing in it, but they do have blank templates that you can use as well. And on one of these learning shapes, we have all of those 7 reasons that I just laid out for ocean exploration. And on the other one, we have some different facts, things like the challenges of working in extreme environments like the deep ocean stimulate technological innovations. Now, each one of these statements on this cube over here corresponds to one of the reasons on here that we explore the ocean. So what you're going to do, this is a game that you can have your students or your kids compete with. You're going to roll this shape, see what it lands on. I got in deep cold water, methane gas is trapped inside frozen methane hydrates. So why does that matter? What does that have to do with ocean exploration? What's the reason that that's important? So looking at our cube, methane hydrates are a potential energy source someday. And maybe I'll get used to this backwards camera view. But methane hydrates can be used to generate energy. So that's a possible way that we can expand our energy technology in the future. So you can have multiple cubes with the reasons on it, so you can have multiple students competing at the same time to figure out the right reason that statement goes along with. You can also have them just find pictures that represent each of those reasons. So something like this right here, that would be that methane hydrate that's actually being burned and giving off a flame that could be used to produce energy. You can use those example learning shapes that are in that lesson plan, or using the blank one, you can have students research it for themselves and come up with something that corresponds to each of those 7 reasons that they can put on the cube themselves and build that learning shape on their own. Give them a little more ownership over the activity. So that's our very first activity. Why do we explore? It's important to understand, even though we love the ocean, most people that are watching this would love the ocean as well. It's important to give those reasons, those real concrete explanations of why other people should care about it. Why does it matter? Why do we spend so much money on this? And why have people throughout history focused so much on exploring the ocean? Speaking of people exploring throughout history, one of the things that has remained constant in the need for exploration is some of the technology. So even though we've made leaps and bounds in technology and have crazy underwater vehicles and ROVs and all kinds of crazy technology, something that hasn't changed over time is rope. We've always needed rope. The technology that we use and the way it looks and everything that it can do has changed over time, but from the earliest ocean explorers, people have needed to make some sort of rope or fiber. You can use it to anchor your boat, you can use it for rigging your sails, all kinds of things. So this activity is going to be creating your own rope. I'm kind of cheating because I'm starting out with something like yarn that is already pretty well established and built. But what you're going to need to do is cut 9 lengths of this rope. I cut mine to about that length, maybe 3 feet, 2.5 feet, something like that. I'm not great at estimating lengths, but something around there. You can change the length depending on how long you want your rope to be. And you're going to tie all of those 9 strands into a knot together. Once you have it tied in a knot, you're going to separate it into 3 groups of 3. And I set this up ahead of time so that you didn't have to watch me twisting a bunch of string for too long, but I'm going to get behind here and finish up. So I've already done this with 2 of my 3 groups of 3. But you're going to take each of those groups of 3 and twist them together. You want to twist them all in the same direction. Each of those 3 groups should be twisted. I'm doing all of mine clockwise. You can do all of them counterclockwise, but you want to keep track of which direction you're twisting your rope. Now, like I said before, yarn is already nicely wound together, but throughout history, sailors and mariners have used things like palm fronds and different fibers from nature. You can use all kinds of different materials to make rope, and they had to back in the day before they had lovely manufactured strings and fibers. All right, so you want to twist that strand until it just starts to bunch up when you fold it over onto itself. You want to see it coiling on itself. And then once you have it to that point, you're going to tie off the end of it. Now, like I said, I've already done this with my other 2. So I'm going to take all 3 of my coils, and since I had done them clockwise before, I had twisted them, now I'm going to twist them the opposite direction, counterclockwise. When you just have one strand of rope or of twine or whatever fiber that you're using, it's much weaker than putting it all together. So if people wanted to haul heavy loads or they needed to attach an anchor or something heavy, it was important to have something stronger that's not going to snap under the pressure. All right, now I think I've just about got it all twisted up. You are going to lose a little bit of length when you do that, but that's okay. You want to make it a little bit longer at the very beginning when you actually want it. Now that I've got it all twisted up, I'm going to tie all 3 of those together, and now I can safely let go of it, and it won't uncoil. So I started out with 9 different strands, and now I have one nicely coiled rope that's much thicker and much stronger. Once you've created your rope like this, you can use it to practice different knots that people would use in order to do those things like tying off their boats or attaching sails or attaching equipment. So things like submarines, you don't want them to just disappear if it's a submersible vehicle that you want to get back. So you have to have some sort of tether to keep it attached to wherever you can get it back from. So you can use this to practice all of those mariner's knots, all of those sailing knots. That it's kind of something fun to do with your hands, and it's kind of like making a friendship bracelet almost. It looks pretty cool. You can change up the colors of it and make rope bracelets if that's what you wanted to do. Make it into a summer camp activity from your own home. So that's our next activity there. Now, so that's one of the technologies that has remained constant throughout human history in ocean exploration. The next thing we're going to talk about are some challenges that explorers have had to face. So obviously up at the surface of the water, we're at atmospheric pressure. We're not worried too much about getting crushed on a daily basis. I'm not too worried about getting crushed at sea level. But as you go down in the water, all of the weight of that water is going to be pushing down on you. Some animals have adapted to live in these deep environments, but we are not adapted to live there. So if we were going to go down in vehicles like the Alvin, this is the Alvin, which is a human-occupied submersible vehicle that's out of the Woods Hole Oceanographic Institution. They use it for all kinds of research. You can go down to extreme depths in the Alvin and really get that up close and personal, firsthand interaction with the ocean's floor. But when you do that, if you take a deep breath in and out, your lungs are expanding and contracting, and inside your lungs is air. What we're going to be doing is making a Cartesian diver, which demonstrates why the air in our lungs and in all of our tissues would have some issues at depth. So all you're going to need for this activity is some sort of compressible bottle. You can use a plastic water bottle or a Coke bottle, something like this, and you're going to fill it most of the way up with water. You're also going to need an eyedropper or something similar. You can use a pipette, but you want something with a good amount of weight to it, so a glass eyedropper is perfect. And then some extra water. So I'm going to fill up my eyedropper about 3/4 of the way up with water. You want it to get all up in that bulb as well. But the goal is to have it just floating up at the surface of your bottle. So let's see how I did. All right, perfect. So it's floating just at the surface. It didn't pop up immediately, but it is still floating. You don't want it to sink down to the bottom. You don't want it completely full. But now that you have it in your bottle, what you're gonna do next is squeeze your bottle. And you can see that that pipette, that eyedropper, plunged down to the bottom. This is a great inquiry-based activity that you can try to get your students or your kids to figure out why this is happening. Why, when you squeeze on this bottle, why did that eyedropper go down to the bottom? What about it is making it do that? What are you changing? So it turns out, I did this with another one. I wasn't sure if this one would work out in the moment, but it turns out it's a pretty reliable experiment. So what you're seeing in this bottle is when you squeeze it, you are increasing the pressure inside of this container. Water is an incompressible fluid. It means no matter how much you push on it, no matter how much water there is, it's not going to change its shape or its amount of volume that it takes up. What does change is the air that you have inside of the top of this eyedropper. Inside of that bulb, you have that little headspace of air that is being compressed. So if you think back to when we were talking about breathing in and out, those air pockets inside of your body will be compressed as you go down to deep, deep depths. A great example of that happening is this right here. So it might look kind of crazy because it is kind of crazy, but this right here actually went down on the Alvin. It was attached to the basket here. It was in a bag with a bunch of other styrofoam containers. So this was a styrofoam wig head. If you look at it compared to the shape and size of my head, this used to be the same size as my head. But when it went down to that depth, all of the air that was in those spaces between the styrofoam got pressed out and came out of this styrofoam, leaving behind a much harder, more compact solid. So that's going to be a big problem if you're trying to go down to depth if you're going thousands of meters under the ocean surface, you don't want to get squished because it's not going to feel too good. It also works the other way too. So when you're ascending, the air inside is not being compressed as much, so it's going to expand, which is why scuba divers have to be really careful when they come up, because that expansion and contraction happens on your body and your air cavities and not on the water around you. All right, so the way that scientists have come up with that, with ways to deal with that, is pretty ingenious. There's all kinds of burping and air compression that you can do to counteract all of those issues that you would face going down to depth. But because of the inherent risk of things like this, a lot of scientists and researchers are switching to using more mechanical-based technology, things like ROVs, remote operated vehicles, instead of HOVs, or human-operated vehicles. So you can switch to less risky in terms of human life technologies, and a lot of people are doing that. With increasing and more advanced technology being developed every day, there's not as much need for people to go down into those spaces, although there is still something to be gained from having those eyes on the environment that you're studying and getting a firsthand view of those areas that are important to you. All right, I had a question come in. Let's see here. Excuse me, reading. What do you think is the next area of exploration? That's a great question. So I mentioned before that only about 5% of the ocean has been explored. There's a lot of places for us to explore, but one of the things that I think is going to be a huge focus, and I'm not in charge of deciding who does what in research, but something that's really important to people is human health. There's a lot of really interesting biotechnology that has taken inspiration from the ocean. In coral reefs, there are all kinds of chemicals that have been used for developing new medicines. So I think that biotechnology is going to take a lot of cues from the ocean, and it has a lot of monetary impact on those technologies, and it gives people an incentive to fund that exploration and learn a little bit more. All right, we have another one. What are some other types of equipment used for exploration? So we have that HOV that I mentioned before, that human-operated vehicle, ROVs, which are remote operated vehicle, AUVs, which are autonomous, I don't remember what the U stands for, maybe Evie can help me out in the comments here, but autonomous something vehicle, and so that would be something that can move on its own, doesn't need to be piloted like a remote control vehicle. There's also things like gliders, which are released and they have their own kind of propulsion system that either relies on currents or wind or some sort of passive system that will be gathering data constantly, and then they can transmit that data to the satellites and then get it to a different location on land to use for research. There's all kinds of crazy research technologies that are really, really cool. There's a website, the Ocean Explorer NOAA website has a whole lot of information about technology. A lot of these lesson plans are hosted on that website, but their homepage has a lot of information about new technologies as well as career paths that you can go into with this. And then, oh yeah, thanks Evie, autonomous underwater vehicle, that's AUV. All right, let's see, what other question? There were a couple more. Can you use food coloring for the Cartesian diver to show the eyedropper? Absolutely. So say you were using a plastic pipette, a clear pipette, instead of an eyedropper with a black bulb that you can see. You could fill it with colored water rather than clear water. You'll actually see that the water isn't changing places as well. So that would be an interesting way to visualize the incompressible nature of that water. And then it would help you see the pipette go up and down easier as well. Great idea. And then what depth did the Spider-Man head shrink? Let's see if I wrote it down. So this one, I can tell you what dive it went on. It went on Alvin dive 4679, and it went to the bottom of the Gulf of Mexico. I don't remember exactly what depth it went to, but it was more than 1,000 meters. I want to say it was like 2,000 or 3,000 meters, but I don't remember off the top of my head. But Alvin dive 4679, maybe 77. It's kind of hard to read at this point since it got really crinkly, but a couple thousand meters is what I believe it went to. This was back in 2014 that I did this. What's interesting is on here, if you look closely, there's puncture marks all over it, which is so that that air can escape uniformly. If you just send it down as is, air doesn't always come out uniformly without those nice even spacings to come out of, and so you might end up with a weird lumpy head on one side, so you try to make sure that it comes out nice and symmetrical. It's actually something that research scientists do a lot, even without Alvin, using something called a CTD, or a conductivity, temperature, and density rosette. So it's a big assembly of a bunch of bottles that you can send down, and the CTD just measures the water properties, and then those bottles take water samples, but that goes down to extreme depths as well. And so you can attach bags with all kinds of styrofoam cups. If you know a researcher who goes into the Gulf or into the ocean and does water quality kind of experiments, a lot of times classes have given them bags of styrofoam cups to send down, and it's a really cool demonstration. I don't know of anybody off the top of my head who can do that for you, but if you do some research into your local institutions and see what researchers are doing water column studies and going out onto ships and doing this kind of research, a lot of times they will take things from land, space allowing, and put them down into the bottom of the ocean. It's very cool. All right, back to our last activity here. Like I said, it's a topic near and dear to my heart, so I can ramble about ocean exploration for a very long time. So I'm going to go over our last activity here. This one's all about visualizing in the ocean. So we don't always have access to things like the Alvin or vehicles that you can go down onto. So how do scientists see to the bottom of the ocean? And this is not going to be something that scientists would use necessarily, but this is something that you can use at home with your kids. Say you're going to the beach or you're going to a lake or a stream and you want to look down into the water without getting super wet. You can use a can. This is a coffee can, and then I cut off the bottom of it with a can opener. You want to be careful with the edges of the piece that comes out. They are pretty sharp. So make sure that your kid is supervised while they're doing this so they don't hurt themselves. And you're going to need some saran wrap, some cling film, and a rubber band. It's pretty simple. You can do it with other containers too. You can do it with just a tin can, but something with a little bit of depth is best, not something that has some height to it. And you're going to take this saran wrap and place it over the top of your can. And you're going to fasten the rubber band around it. So it looks like this. I have my nice covering of my saran wrap on top and my rubber band holding it in place. Now what you've created is a viewing scope. So you can put this down into the water with this side facing down, and it gets a little bit deeper than the naked eye can see, and it eliminates the diffraction and the distortion that happens from the water. And if the water is murky, you can also see a little bit clearer because you're not looking through all of that sediment, all of that turbidity in the water. So you can use this, dip it down into the water, and then look through, kind of like a glass bottom boat, what's down underneath there. And like I mentioned before, this isn't necessarily something that scientists would use in the field because it's a little bit tricky to make something deep enough to see the areas that they're trying to get at. So scientists have to be a little bit more creative. They're going to use something called multi-beam, which is a sonar array that bounces sound onto the bottom of the ocean, and it bounces right back up into a collector, and so they can get a map of how long it takes for that sound to bounce back, which gives them the depth of how deep it is in that specific area. So you can get really high resolution maps of the ocean's floor in order to figure out what areas look interesting for study. I believe it was the Okeanos Explorer recently went off of the Carolinas coast, the southeast coast here. I believe it was last year. Had an expedition off of our coast because a lot of that had never been mapped. So something that's so close to very populated areas of the United States hasn't even been explored. So you can imagine if that's not explored, then of course there are huge amounts of areas that haven't been explored throughout the ocean. So they went off of our coast and mapped out a bunch of interesting sites, and from there they had discovered some sites that they wanted to study a little bit further. They studied a shipwreck that was down at the bottom. You can get enough detail to see a shipwreck, which is amazing. From one of the, I don't remember, I'm bad at history, but you can look at the details of that voyage and find out more about what they mapped. You can also get as high definition as to see a bubble plume coming off of the ocean's floor. So bubble plumes happen in the Gulf of Mexico, especially where methane is coming out. We all know that the Gulf of Mexico has all kinds of oil and gas reserves, but along with those oil and gas reserves are methane hydrates and methane seeps. So those gases coming out of the ocean's floor. And you can see where those bubbles are coming out, and it gives them a little bit more of a target to figure out, okay, what areas do I want to study more? So you can use that, just pass over running that multi-beam, running that sonar, in order to find out more information to guide future studies. So there is an activity on the Ocean Explorer website, which Evie has linked on the side there. That's all about bathymetry or seafloor mapping. You can get some really, really cool images on your computer. There are some programs that you can visualize that data and map it out and get a little bit more of a hands-on experience with that mapping technology. It's a little bit harder to demonstrate in person than it is to look on that website. Oh, Evie has linked a methane bubbling up link over there. I highly encourage you to check it out. It's very, very cool looking at those underwater communities. Another resource that I highly recommend is the Evie Nautilus, which I didn't give Evie in advance to link to you, so maybe she can find it real quick. But the Evie Nautilus does a lot of streaming of their expeditions, and then looking at the Okeanos Explorer videos as well. They're just incredible. So even if you're not interested in the science of it, visually it's just stunning to look at these deep sea creatures. So check those out. All right, I'm just about out of time, so I'm going to open it up to see if there are any more questions. I know that we answered a few along the way. I like to do it while we're going, so that it's a little more relevant to what we were just talking about. But if we don't have any more questions, I want to thank you guys so much for following along with us. Like I said, this is our last in our Educator Helpline series, but I encourage you to continue exploring both the ocean with your newfound technology, and I encourage you to explore our other videos so you can see the other activities to study the ocean and learn a little bit more about what makes it so special to people like me and Evie and everybody else here at Sea Grant and NOAA. It's an amazing thing, and we hope that you guys appreciate it as much as we do. But thank you so much for following along with us and coming back week after week if you haven't. And if not, maybe you will in the future and get to know us a little bit better. All right, with that, I'm going to sign off. Thank you guys so much again, and if you have any questions, please don't hesitate to go to our South Carolina Sea Grant Consortium website. It has our contact information, and it has a lot of other education resources on it as well, so that you can look into those and get an even more detailed way of engaging with the ocean, learning about how you can help. Have a wonderful summer, and we'll see you later. Bye, guys.